A population is modeled by the differential equation dp dt equals 0.09p minus 0.0001p squared, and because this is a population model, we can assume p is greater than 0. We're asked to determine the value of p where the population is at equilibrium, and also when the population is less than the equilibrium population, the population is increasing or decreasing. The given differential equation is an autonomous differential equation because it fits the form dp dt equals f of p, where dp dt is equal to only a function of p, and the independent variable t only appears in the derivative. The equilibrium solutions occur where dp dt equals 0, and if dp dt is greater than 0 or positive, p is increasing, and if dp dt is less than 0 or negative, then p is decreasing. So to find the equilibrium population, we want to set dp dt equal to 0 and solve the resulting equation. So we'd have 0 equals 0.09p minus 0.0001p squared. Notice how the right side is factorable. Let's go ahead and factor out the common factor of p. So we'd have p times the quantity 0.09 minus 0.0001p. So this product equals 0 when p equals 0, or when 0.09 minus 0.0001p equals 0. Solving this equation for p, let's add the p term to both sides, which would give us 0.09 equals 0.0001p. And now let's go ahead and divide both sides by 0.0001. Simplifying, we get p equals 0.09 divided by 0.0001 is equal to 900. So algebraically, the equilibrium solutions are p equals 0 or p equals 900, but because we're told p is greater than 0, the population is the equilibrium at p equals 900. And because this differential equation models logistic growth, we can also call this the carrying capacity, which we'll come back to in a moment. Now the next step is to determine whether the population is increasing or decreasing when the population is less than the equilibrium population. So to answer this question, we want to determine the sign of dp dt over the open interval from 0 to 900. Again, we know p is greater than 0. So if we determine the sign of dp dt in this interval, we'll know whether the population is increasing or decreasing when the population is less than the equilibrium population. So for a test value, let's use p equals 100. So we need to define the sign of dp dt when p equals 100. Well, that'd be equal to 0.09 times 100 minus 0.0001 times 100 squared. So 0.09 times 100 is equal to 9. To find this product, 100 squared is equal to 10,000, and therefore to find this product, we can move the decimal point 4 places in this decimal here, which would give us just 1. So we have 9 minus 1, which equals 8. So because the derivative is positive at p equals 100, it's positive over this entire interval, which means the population is increasing when the population is below 900. Let's check this graphically by looking at the slope field generated by the differential equation. We found the equilibrium population to be 900, which is verified by the slope field. We can tell the population is increasing when the population is below 900, because notice how all of the slopes of the segments are positive. We can also verify when the population is above 900, the population is decreasing because all these segments have a negative slope. Before we go though, I'd like to look at this problem in another way. The given differential equation does model logistic growth. So if we write this differential equation in this form here, we can identify K, the carrying capacity, which is the equilibrium population, as well as the intrinsic growth rate, which would be the growth rate minus any constraint. So let's just show how we can write the given differential equation in this form here and also answer the same two questions. So starting with the given differential equation, we want the right side to be a p term times the quantity 1 minus another p term, which means we'll factor the right side and factor out 0.09p. This would give us dp dt equals 0.09p times the quantity 1, which we need, minus, now factoring out 0.09 from 0.0001 will leave us with whatever we get when we take 0.0001 and divide by 0.09. So using the calculator, notice that 0.0001 divided by 0.09 gives us this decimal, but if we press math, enter, enter, we're left with the fraction 1/900th. So if we factor out 0.09p from 0.0001p squared, we're left with 1/900th p, or just p divided by 900. Notice how now the differential equation is in the form shown here for the logistic growth model. And notice how once it's in this form, we can easily identify K, the carrying capacity, is equal to 900, which is also the equilibrium population. And this question doesn't ask, but R, the intrinsic growth rate, which again would be the growth rate minus any constraint, would be equal to 9%. To answer this last question again, we still have to select a test value in the open interval from 0 to 900. So again, if we use 100, we'd have 0.09 times 100 times the quantity 1 minus 100 900ths, or 1/9. Notice how each of these factors would be positive, and therefore dp/dt is positive in this interval, which again verifies the population is increasing when it's below the equilibrium point. So not all autonomous differential equations model logistic growth, but in this case it does, so we do have two possible approaches to answer this question. I hope you found this helpful.